Hi, my dear students. Welcome to Unacademy. Welcome to Dakshina Engineer Junction, where you learn the concepts well in a very easy manner, in detailed manner, and these concepts are very much helpful for the any competitive exams like GATE, ESE, ISRO, DRDO, and state government GENCO, TRANSCO, and central government SSC, JE. And here we are ready to help you in all this in this particular concepts, all the technical concepts we are ready to help you. And if you need any particular topic, and do comment in the comment section, we are ready to help you in those concepts. Fine, let's continue our discussion. And today's topic is stability analysis. Stability, this is one of the most important topic in the signals and systems and control systems also. And see this thing here, stability. What is meant by stability here? The system, what are the system we have designed, and we need to take care of that the system must be stable. And let us consider this is my LTA system, and having the impulse response is H of t. This is LTA system. I want to analyze the nature of this system. We need to analyze it. Whether this system, this box is stable or not, we need to analyze. For this, we are going to see the different cases we are going to see. Now, so if we know H of t well and good, we can, with the help of the H of t, we can analyze. If we don't know H of t, let us consider X of t is my input and Y of t is output. By using the, if I know the input and output relations, we can able to analyze the nature of the system. Okay, without knowing the H of t, from the X of t to Y of t, we will analyze the nature of the system. Right, see here, as we know, Y of t, which is given as H of t convolution with X of t. Now, H of t, where this X of t is what you tell me now, input, and H of t, which is belongs to the system, that is called as an impulse response. That is what you tell me, impulse response. Now, here what we are going to do here, so generally we are going to analyze the nature of the system with the help of H of t. If we don't know the H of t, from the using the input output relations, we can able to analyze. Let us see this thing, how we can able to analyze the stability of a systems in the different ways. Here we are going to see that there are 6 different ways we can do the analysis of a system stability. The first one is, if I know only input output relations, if I don't know any impulse response or transfer function, then we can do by using the input output relations. Second one, if I know the impulse response, we can do, and with the help of the poles, and with the help of the ROC, with the help of the transfer function for the discrete case, and ROC of H of Z. Shall let's see this thing. First one, with the help of the input output relations. Here basically, as we have seen, the output of the system Y of t, which is given as H of t convolution with X of t. Here, where this X of t is an input signal, and which will maintain this X of t is a bounded. So this X of t, which we take it as a bounded signal, means that is a finite signal. Bounded signal, finite signal, stable signal, we can see this thing. If this is stable signal, then and we are going to see this thing here, whether this y of t is stable or not, bounded or not. If for in case of a x of t is bounded, if the y of t is also bounded, then I can say that this h of t is bounded. That means system is bounded nature. So this type of stability, which we can call this as a BIBO stable. That is, if for in case of a bounded input, if the output is stable, then we can call this as a BIBO stable. Now let's see how we need to analyze it. Let's take some examples where y of t is given as a 10 into x of t. First of all, here you need to see this thing. This is my x of t given, and this is what you tell me now here, input, and this is my output. Right. Now we will apply a bounded input. We apply bounded input means what you tell me now here, the value of my x of t must be stable. We need to apply the bounded input. We apply the bounded input means, let us consider this x of t, the value which is a value that is something, value, it is bounded value bx, and where this bx is less than infinity. Bx value is a finite, consider, where bx is a finite. Now you see this thing, if you have taken this as a mod on both sides, then see what I will get now here, mod of y of t, which is equal to mod of 10 into x of t, right? Now, so what I will get now, this is 10 into mod of x of t, that is magnitude. So then, so you tell me now here, the magnitude of y of t, which is given as 10 into the maximum value. The maximum value of x of t is what we can say now here, less than bx. Maximum value we can take it as a maximum of bx. Now you see this thing, this is a finite value, isn't it? Now 10 into finite is a finite only. Now so from this what I can say, this value, I can say this is a finite, I can say, now tell me. From this I can say finite. So that means what I can conclude, you tell me now here, the given system is stable. Given system is BIBO stable. Given system is BIBO stable. Next, now let us see the next one here, x square. Here also we can take this as, for the bounded input, input must be bounded, which we have taken as something bx value, and that bx value less than infinity. Now if I take this mod on both sides, magnitude we have considered here, so this is what it is now here, that is mod of bx square now here, the square of the finite value, so which will give us a finite value only now. This is a finite value, square of the finite value, finite only. So that means I can say my system is BIBO stable. The system is BIBO stable. Next you tell me now here, in these cases. Now here we have taken the bounded value of x of t, which is less than bx and which is less than infinity. Now you tell me now here, what is the value of mod y of t here, which is given as mod t into mod of x of t. Now if we see carefully, this is the magnitude of y of t, which is given as into mod x of t. Here this magnitude which is equal to bx, and here we can change the time parameter from way to way, minus infinite to plus infinite. minus infinite to plus infinite we can change. So when I change here, t is from minus infinite to plus infinite. If I change the t value from minus infinite to plus infinite, what happened to this y of t here? Then you see this thing here, the magnitude of y of t. So when the t tending to infinity, so this y of t value tend to infinity now here. When t tends to infinity, y of t tending to infinity. Here x of t we have taken bounded. So because of this input is bounded, but because of this t at the time tends to infinity, this value become infinite. So that's why what I can say now, this is the given system is unstable. It is not BIBO stable. Input is bounded, but it is not stable. Right. And if you see carefully, ln of x of t. Now you see, I can change the different values, bounded values for x of t. Now, as you might know, the nature of this log function, if I take that t, no, this here we have taken this as x of t I have taken, and this is ln of x of t. Now this nature is log 1, when x of t is equal to 1, so it is touches to 0, log 1, and so this value which is like this is the log 1. And if you see carefully, what is the value of log 0? It is minus infinity. Here at this location, x of t is how much you tell me, which is equal to 1. So at this location, so here x of t, how much you tell me now, which is equal to just 0 plus I can consider. Now you see this thing here, when if x of t which is equal to 0 plus, what happened to y of t you tell me, which is ln of 0 plus ln of x of t. So this value which is equal to minus infinite. Here this input x of t is a bounded only. Input is finite value, but y of t we are getting infinite now. So what I can say, the system is unstable. The system is unstable. Next one. Here you see carefully, in this case, y of t is equal to cos of x of t. As we know here, this is cos theta. The range of cos theta, which is from minus 1 to plus 1. Range of cos theta is always from minus 1 to plus 1. That means if we take any value of x of t, the output, that is y of t, should be always like this only now. I can write now here, so this is cos of x of t. This lies only from minus 1 to plus 1. That means range of here minus 1 less than y of t. We can pay r equal to also. Less than or equal to 1. The value of y of t, which is always less, lies between minus 1 to plus 1 for any values of theta. So from this, what I can say, in this case, the system is stable, isn't it? Like this manner, we will analyze the stability of a system if they given input-output relations. Now let's see the next thing here. When the impulse response is given, impulse response means what you tell me now here, h of t. When h of t is called as an impulse response of the system. Now let us see this thing here, how we can do here. If the given impulse response of the system is given, Yes, if integral from minus infinite to plus infinite h of t into dt, if it is a finite value, if it is less than infinity, then I can say system is stable. Then I can say system is stable. Stable system. This is for continuous case. The same thing we can do for the discrete case also. And for discrete case, what we can do here? And for the discrete case, sigma n is from minus infinite to plus infinite. That is mod of h of n. This value must be finite. Mod of h of n, this value must be finite. Then I can say the system is stable. Okay, all of you tell me discrete case and continuous case. Let us see some examples here. Look at or check whether the system is stable or not. Here they given what they given. We don't know input output relations. We know impulse response, and it is a continuous now here. So what is the condition for the continuous impulse response? Must be stable. When h of t into dt, that must be a in less than infinity, means we should get that is a finite value. Now tell me now here, I can do this thing integral. We have u of t is there, limits are 0 to infinite only now. H of t is e power minus 4t into dt. Now you tell me now here, e power minus 4t by minus 4 limits 0 to infinity. So that is minus 1 by 4 into, when I subtract the upper limit, e power minus infinite minus e power 0. So what I will get, you tell me now here, minus 1 by 4 into which is 0 minus 1. So which is equal to plus 1 by 4. And this is a finite value, now tell me. This is a finite value. So then I can say the system is stable system. Since it is finite value, we can say it is a stable system. Now let us take the next problem. H of t is given as e power 4t. Now here also integral from minus infinite to plus infinite. Impulse response only given here also. This must be, we need to get finite value, we need to get. Let us check this thing whether it is a stable or not. And integral, I can say 0 to infinity, I can say 0 to infinity, and e power 4t into dt. E power 4t into dt, which is given as what I will get. E power 4t by 4, and the limits 0 to infinity. Now substitute the limits now, that is 1 by 4 into that is e power infinite minus e power 0. Now you see this thing, what I will get now here, 1 by 4 into e power infinite is a infinite minus 1. So this means which we are getting this as a infinite now here. So this is impulse response is infinite, so that's why the system is unstable. All of you. So if they given impulse response, we need to analyze like this. Next, now here is a discrete case is given. Now let us see in this case how we can analyze it now. Discrete case. H of n is given. So that is summation sigma n is from minus infinite to plus infinite. That is mod of h of n must be a finite. It is less than infinity. This must be a finite value. This is a condition for the stability. Right? Yeah, here also we have a mod. Okay, this magnitude is same will come now. This is a mod. this mod is up to here. Okay, magnet. Yeah, now you tell me now here in this case. So here we have u of n is there, so the limits I can say n is from 0 to infinity and 1 by 2 whole power n. Now when n is equal to 0, which we will get it as 1, and this is 1 by 2 plus 1 by 2 square plus 1 by 2 cube. Like this will come, which is given as, it is geometric series now here, the infinite geometric series mod r is less than 1. So what I can say now here, a by 1 minus r. So which will get this as a 2. So, and this is a finite value now, tell me, which is a finite. So that means what I can say here, then stable system. So I can call the system is stable. Fine. In this manner, we'll analyze if impulse response are known. Now let us see if they given the poles of a systems are given. In this case, if the poles of a systems are given, now the condition is, now this condition here, and this is my S plane, and here it is a real part of S, and this is imaginary part of S. This is the origin, and here, which is, this is called as a left of S plane. This is called as a left of S plane, and this is called as a right of S plane. Right of S plane. Simply we'll call this as a left of S plane, which to call LH plane, which to call, and this is called as a RH plane, RHS plane, right of S plane. And here this is a real axis. This is a real axis, and this is an imaginary axis, j omega axis, or we can call this as an imaginary axis, j omega axis, or we can call it as an imaginary axis. Right. Now, if all the poles of the system, means transfer function, if it lies only in the left of S plane, if all the poles are lies in the left of S plane, then I can say the system is stable. If all the poles of the transfer function H of S lies on the left half S plane, then the system is stable. Here all the poles must be lie on the left side only. So in this region only has to lie in the left of S plane, then only it is a stable. Okay. Even the pole should not lie on imaginary axis. If the poles lies on imaginary axis, then the nature it will comes to the marginally stable. If the poles lies on the right of S plane, the system is unstable. Okay. Now let's see this thing here. And take this problem here. They given the impulse response Laplace transform is given H of S, which is given as 1 by, I can convert the partial fractions, which is equal to S plus 2 into S plus 3. Now you see, tell me the poles of the system. poles which is equal to S is equal to minus 2 and S is equal to minus 3. These are the two poles which we have, right? And this is the real part of S and this is an imaginary part of S. And you can tell me now here the poles S is equal to minus 2 means here we have a pole now S is equal to minus 2 here and S is equal to minus 3. Here we have another pole. So where we lies the two poles now here? The two poles are in the left of S plane only now here. Yes, we don't have any pole on the right of S plane or the imaginary axis. So that's why what I can say the nature of a system is a stable system. Next. Now you see this thing H of S, what they given. If I do factorizations, you can see now here this is S minus 3 into S plus 2, isn't it? These are the roots now. Now you see the poles of the system here. So one is at S is equal to minus 2, the other one is at S is equal to plus 3. Now this is my real part of S and this is imaginary part of S. And so this is called as here, this is my left of S plane and this is right of S plane. And this is a imaginary axis or j omega axis. You see where we have poles, you tell me now here. So the one pole which is at S is equal to minus 2. One pole is here now S is equal to minus 2 I can say. Other pole is at S is equal to 3. Here we have another pole. So we have this pole is one pole in the right of S plane. The right of S plane pole will make the system is unstable. So what I can say? The nature of a system which is an unstable system. Fine. Now let us see the next one. Another way of analysis. If the ROC of a system is given, so what we can do? If the ROC of a system is given, ROC means region of convergence. So then what the condition for stability is? If the ROC of H of S includes j omega axis. J omega axis means what? Imaginary axis. Include j omega axis, then the system is stable. Then the system is stable. If the ROC include the j omega axis, then only the system is stable. If the ROC does not include the j omega axis, then the system is unstable. Then the system is unstable. Okay. Now let us see some examples. Yes, so now see in this problem here they given the H of S which is given as, you tell me, look at now here, the roots are S minus 3 into S plus 2. These are the roots now here, and you can see the poles now here. We have two poles, one is at S is equal to minus 2, the other one is at S is equal to 3. Okay. Now look at this thing here. First of all, I want to see one by one carefully. First case now here A. Yes. So first of all you locate the poles now here. I am locating the poles. so that all the three are in this here only. Okay, look at now, this is my S plane. Here what are the poles here is there? One pole is at S is equal to -2 here. This is S is equal to -2 here, we have one pole. The other pole is at S is equal to 3. The other pole is S is equal to 3. Isn't it? All of you tell me first thing. Right, here we have the poles are like this. Next, now you see carefully now here, what is the ROC of a system is given. So here, which is equal to ROC, real part of S, this is the real part we should take now here. The real part, this is on x-axis, we will take the real part of S. This is a ROC. Real part of S is what you tell me now, greater than 3. Means, how this ROC you see carefully. So, means, from here to here, so this thing will draw a line. How this ROC here tell me? Greater than 3 means right side or left side? Which is right side now like this. Greater than 3, which is right side like this. This is a ROC of a system. Isn't it? This is a ROC. This is the ROC. Now you see this thing here. What is the condition for stability now here? ROC must include the j omega axis. And here this is a j omega axis now. This is a j omega axis, isn't it? Is the ROC include the j omega axis? No. ROC does not include a j omega axis. So what I can say, the nature of the system is unstable. Since ROC does not include the j omega axis, so the system is unstable. Now you tell me the second case now here. Now in this case, second case, see what's going to happen here. Here they given this ROC which is given as less than -2. Tell me here what happening. And this is a real part and this is a imaginary part. This is the imaginary axis. This axis which is called as a j omega axis. J omega axis. Now you see carefully. Now here what happens now? First look at the poles here. We have one pole is at S is equal to -2. The other pole is at S is equal to 3. Right? Now you tell me in this case what's going to happen. So this ROC is less than -2. Tell me the ROC is less than -2. So means left side or right side, you tell me. Left side. So which is like this now here. This is my ROC. Left of smaller than -2 means like this now left side. Right. This is the ROC. Now in this case, is the ROC include the j omega axis? ROC in this case also ROC does not include the j omega axis. So what I can say, the nature of a system now tell me, unstable nature. The nature of a system is what I can say, unstable nature. Now let's see the next case now here. Now third case, ROC lies between -2 to this make it as +3, not -3. Do correct it, +3. Okay, in this case, let's see this thing here. Now, in this case, -2 less than real part of S less than 3. So, in this case, how we have? Here we have the poles. This is my real part of S and this is imaginary part of S. Here tell me the location of the poles. One pole is at S is equal to -2. The other pole is at S is equal to 3. Now you tell me here where is the ROC is given lies between these two. Means ROC which is like this, you tell me, which is more than -2 less than +3, means this is a ROC. Now tell me, this is a ROC. You can see carefully, this is a ROC of a system given. This is a ROC. Now you see this thing is a ROC include the imaginary axis now? Yes, so that's why the system is stable. So that's why the system is stable. In this manner we'll analyze it now. Fine. Now let's see the another way here. So Laplace transform, that is for the continuous cases. For the discrete case we'll go for the Z transform, H of Z. You see here when the poles of H of Z is given. So in case of a Laplace transforms, so here j omega axis we need to do. In case of a Z transform, we have a unit circle is required. Means here what the condition here? If all the poles of H of Z lies inside the unit circle, then the system is stable. So in the Z plane here, which is called as a real and this is a imaginary axis, here we need one circle, that is unit circle is required. This thing, if I call this is a unit circle. Now all the poles must lie inside the unit circle. All the poles of a system must lie inside this unit circle. Then only the system is stable. Right? Now let's see some problems. Take this thing here. Now this given H of Z or X of Z is given. Tell me now X of Z, which is given as 1 by Z plus 2 into Z plus 1. Now you can see the poles of the system here. One is at Z is equal to -2. The other one is at Z is equal to -1. Now, so you can do simply what we can say here, mod Z you can do. Mod Z, how much here? Tell me, 2. And this is mod Z, which is equal to 1. Right. Now you will see this thing carefully. Now this is a real part, real axis, and this is an imaginary axis. Now you see this thing, I have drawn, this is my unit circle. This is a unit circle. So here this magnitude, so this here at this location, how much is mod Z value? Which is equal to 1. Now you see this thing here, mod Z is 2. That means this pole is outside now here you see this thing, this is, which is outside. If the pole is outside the unit circle, then what I can say the nature of system, if any one pole lies outside, then it is unstable only. All of you tell me. So then the system, we can call this as an unstable system. Right. Next, in this case, now here also we can see, now here this is mod z value, which we will get this as a 2. By seeing itself, we can able to identify a mod z which is equal to 3. And so what is the condition now here for stability? Now here all the poles must be lie inside the unit circle. So you see this thing here, this is the unit circle. Both these poles are lies outside the unit circle or not. So then the system is unstable. Okay. Done. So this is a way. Now let's see the another one here, last one. If the ROC is given, so let's see how we can able to analyze now. If the ROC is given, then what we can do here? If ROC of the transfer function H of Z includes the unit circle, then the system is stable, if not unstable. Simply ROC include the j omega, previously j omega axis, now it is unit circle. Now check in this case here, and here also we have a poles here, they given the poles of the system here. You can see one is at, so that is z is equal to 2 and z is equal to 0.8. No effect of zeros. Fine. Now take the first case now here. First case here is ROC which is given as a greater than 2. Check in this case now here, this is a real part and here this is a imaginary part. Locate the, so I have taken, this is my unit circle. This is my unit circle. Now you see carefully. So what they given now here at these locations, what are the poles are there here? You see this thing, one pole is at z is equal to 2. One pole is at z is equal to 2. The other pole is at z is equal to 0.8. This is the 0.8 here, isn't it? Here. Right. Now you see this thing here. What they given, the ROC is a mod z greater than 2. So with this I am drawing one more circle here. Now what they given, this ROC is a greater than or less than, here they given ROC which is given as what now here, greater than is given, that means outside here like this now. Now this is this ROC include the j omega axis or not? This is the ROC. Is the ROC include the j omega axis? No. Here in place of j omega axis, here we have a unit circle, not a j omega axis, unit circle. Here ROC does not include the unit circle. This red circle is a unit circle. It does not include the unit circle. So that means what I can say, the nature of the system is now here, tell me, unstable. All of you. Next. Now if you see the second case now here, what they given now here, this mod z which is less than 0.8. Now you tell me in this case what happened? Now we have poles. Now one is at 0.8. So here this is a circle for z is equal to 0.8, and this is the circle for mod z, which is equal to what, 2, right? Now we have the unit circle. This is a unit circle. This is what, unit circle. You see this thing, what they given now, ROC. Here the ROC given less than 0.8, means less than 0.8. This is a ROC, tell me. This is a ROC. ROC. Now you see whether the ROC include the unit circle or not here. In this case also ROC is not include the unit circle. So that's why I can say the system is unstable. Next, and the C case, what they given the ROC, 0.8 less than mod z less than 2 is given. Now you tell me in this case whether this ROC include the unit circle or not. Now we have a poles. One pole is at, this is the circle for z is equal to, so here this is for z is equal to mod z is equal to 0.8, and this is the circle for mod z, which is equal to 2. Now I need a unit circle, and this is a unit circle. Now see this thing, what they given the ROC here, which lies between 0.8 to 2. So here 0.8 to 2 means where the region, you tell me here, 0.8 to 2, like this now. Here this is the region of ROC. This is the region of ROC, isn't it? Now you can see, now in this case, is my ROC include my unit circle or not? Yes, ROC is inside. So here the unit circle is inside my ROC. ROC is included the unit circle. So that's why in this case the system is stable. In this case we can say for this particular ROC the system is stable. Now you see this thing, these are the different ways for the analysis of a stability of a system. You can see with the input output relations, impulse response, poles, and ROC, and discrete as well as continuous manner. Hope all of you like the session. All of you do like, share and comment in the comment section if you need any other specific topic. Let's meet in the next topic. See you, bye bye.